Today we are going to talk about the last two new tests for conversions and divergence. One test is very, very popular. As a matter of fact, when we get into the next unit, we're going to be using it quite a bit. The other one's a little bit obscure, but the first test we're going to talk about, the ratio test, is probably going to become one of your favorites. Number one, it's easy, and number two, it works really well on difficult, yucky looking problems, okay? It says so far there has been no one convergence test that always works, but now we introduce a test that interestingly enough is effective on some of the most complicated series, yet is pretty much worthless on simple series. But for the simple series, we already have something that works. The case in point is to find the convergence of 1 over n factorial. So up to now, we haven't been able to do that. We can do harmonic, we can do n squared, we can do square root of n, we can do all these different ones, but we've never found a test that works on n factorial. It passes the nth term test, which means that it might converge. But then it's not geometric, it's not a p-series, it can't be integrated because we don't know how to integrate a factorial. And the limit comparison test gives us a limit of 0, which tells us nothing. The question was asked last class, what if you did the limit test and you got an answer of 0? It is an inconclusive situation. So that's why I underline this. If your limit is any number other than 0, you are good. And we get that the two functions or the two series do the same thing. But if the limit is 0, it's inconclusive, and that's why we have to go a different route. Yes, sir?
Which test was it that if the limit equals 0 and the terms decrease, then it converges?
Alternating series. If the limit is 0 and the terms decreased, it's alternating. Yes. The ratio test compares the nth term, the formula, to the n plus first term. So basically all you do is you take the equation and you change all your n's to n plus 1. You make a ratio of the two, find the limit. If the limit comes out to be less than 1, the series is absolutely convergent. Also notice one thing before I go farther. Notice that a sub n plus 1 is over a sub n. When we did the direct and the limit comparison test, it really didn't matter which one you put on top or bottom. This one it does. So it must be in this order, and it must be an absolute value. It must be in this order, and it must be an absolute value. If L is less than 1, the series is absolutely convergent. If L is greater than 1, the series is divergent. And if L is equal to 1, the test does not work. Yes?
So if the given series is like sigma a n plus 1, a n plus 1 still going to be on top?
Okay. A sub n is the general way to write a series, just any generic series. But we'll come to some problems where it already has an n plus 1 in it, and I'll tell you what you need to do about that, okay? So, to determine whether this is convergent or not, we examine the limit as n approaches infinity of 1 over n plus 1 factorial divided by 1 over n factorial, okay? So what we're going to do is that means that this one is going to flip over, right? And so that's going to put n factorial over 1 and multiply. So this will now be the limit as n approaches infinity of n factorial over n plus 1 factorial, okay? Now you may be thinking, Miss Bell, you just made it worse. I now have more factorials than I started with. But when you were in pre-cal, everybody that I've talked to about this will attest to this statement. You at one point did some problems that looked like this when you first learned about factorial. 7 factorial divided by 5 factorial. And you would start writing out the bigger one until it matched the bottom. Then you throw a factorial on it. Do you remember this?
Yes.
So those two cross out, and your answer here is 42. Do you see how that works? So you take the bigger one, write it out until it matches the smaller one, and then cross out the factorials. We're going to do the same thing with n's, okay? So what we have here, which one's bigger, n or n plus 1?
N plus 1.
N plus 1. So we're going to leave the n factorial alone. N plus 1 factorial starts with n plus 1 because 7 factorial started with 7. And what's the next one down from that?
N.
N is, and that's what I want. So I'm going to write times n factorial. Okay? So now the n factorials cancel. I'm being very bad here. Got to go back and put the absolute values on. So now after canceling the n factorials, we are left with the limit as n approaches infinity of the absolute value of 1 over n plus 1. What is that limit equal to?
0.
0. Okay? Now, according to the rules, 1 is the dividing line between convergent and divergent. Since 0 is less than 1, and it's good to write that down, that's proving that you know that less than 1 means convergence. So we say, therefore, the series is convergent by the ratio test. So we have now just proven that 1 over n factorial converges. And the ratio test was the best way to do that. Okay? So now what we're going to do is just spend some time practicing on some other ones to show you how they work, depending on where the n is. How do you do it when n's a factorial? How do you do it when n's the exponent? Things like that. So look at number 2. Oops, let me move that back into view, just for those of you who are still copying. Okay? So we now have 0 to infinity of 4 to the n over n factorial. So we're going to do the limit as n approaches infinity. Now, as far as I'm concerned, and until I get told otherwise, I think it's all right if you go ahead, instead of writing fraction over a fraction like they did up here, you go ahead and flip the second one over and multiply. So the first one you do is this one with n plus 1s. So the first fraction will be 4 to the n plus 1 over n plus 1 factorial. That's the one you do first. Then you multiply by the original one flipped over, because it would be on the bottom and then you flip it up and multiply. So divided times n factorial over 4 to the n. Close your absolute value. Okay? Now we just learned what happens with n factorial and n plus 1 factorial, didn't we? So we can go ahead and just mark those out and write what the leftover is. What's the leftover? What was it in the previous problem? N plus 1. Okay? Now let's talk about those 4s. Question?
Where did you get the n plus 1? Why did you change the n plus 1?
Because the formula tells us to. We're supposed to take our sequence and change it to n plus 1s and then divide it by the original. So that's what we're supposed to do in this procedure. Okay? So now let's talk about this 4 to the n plus 1 over 4 to the n. Let's play with it with some numbers. Okay? If you plug in n equals 5, what's the top going to say? 4 to the what power?
6.
Over 4 to the 5th. How do you simplify that?
Just cut that.
4.
It's just 4, isn't it? So how are you getting 4?
Subtract the exponents.
Subtract the exponents. Now, if I had decided to plug in 10 instead of 5, would I have gotten the same end result?
No.
If I plug in a 10 right there, that would be 4 to the 11 over 4 to the 10. Is that still going to be 4? Yes, because the exponent on the numerator is 1 bigger than the exponent on the denominator. So there's always 1 4 left over. Does that make sense? So let's go back to this problem. So that tells me that this is going to cancel this and leave a 4. So I now have the limit as n approaches infinity of the absolute value of 4 over n plus 1. Can I take that limit right now? Yes. What's it going to equal? 0 again, which is less than 1. Therefore, the series converges by the ratio test. Yes, ma'am.
I'm kind of confused about the n plus 1 factorial, like when you cancel it out and then you got the n plus 1.
Okay, if you go back to the previous problem that we did, I know we did it right before lunch, but when you have n factorial over n plus 1 factorial, remember that we just take one of them off, like we did with the 7 and the 5 factorial? Do you remember that previous problem?
Yeah, I remember that.
Okay, So that's what we're doing. N plus 1 is the first one, then we went down 1 to n factorial, matched up with the top, and that leaves just an n plus 1 on the bottom. Okay? All right. Questions? Any other questions? Okay, let's try the next one. Now this one has just a plain vanilla n sitting in there. We do it the same way. We're going to have, I'm going to write down below, limit n approaches infinity. Now remember to change every n to n plus 1. So the numerator will be 4 to the n plus 1. This n will be n plus 1, and then times 3 to the n plus 1. Okay? Always change all the n's to n plus 1 first. And then take the original problem, flip it over. If you don't flip it over, nothing's going to cancel, and then you know something's wrong. So n times 3 to the n over 4 to the n. Close your absolute value. All right, let's tackle what we know. We just did 4 to the n plus 1 over 4 to the n. And when these two canceled out, what was our leftover? Just a 4. Okay, will the 3's do the same kind of thing? Where will the extra 3 be? On the bottom. So 3 to the n plus 1 leaves a 3 on the bottom. Okay, the n's, I can't really cancel anything. So I'm going to leave them there for now. So limit as n approaches infinity. I have 4 and n left on top. Make sure you draw absolute value. And then on the bottom, I have 3 and n plus 1. I'm going to go ahead and distribute that 3 on the bottom without writing a whole other step. So I'm just going to do it right underneath, 3n plus 3, and just mark that out. Save myself some writing. If I plug in infinity right now, am I going to get a number answer, or am I going to get infinity over infinity?
Infinity over infinity.
So how do I tackle that? L'Hopital's rule. Now, I want to show you something. I'm not going to write down L'Hopital's because there are actually some people who can do this in their head, and that will give you straight to the answer. What's the derivative of the top? 4. What's the derivative of the bottom? 3. I'm done. So the absolute value of 4/3 is 4/3.
That's greater than 1. Wait.
Which is greater than 1. Exactly. Therefore, the series diverges by the ratio test. This one's pretty simple, isn't it? The procedure is. The only thing is, if you notice at the original problem, they're ugly. They're extremely ugly, but they clean up so nicely. Any questions on that one? All right, turn over to the back as soon as you're done writing that one down. So, now we're back on number 5. Can we all see? Yes, we can. We're going to actually do 6 and 7 because they bring into play some interesting things. So, we have 3 to the n. Look at what the exponent is already. This was brought up earlier. What if it already says n plus 1? What do? It is n plus 2. You're exactly right. So we do limit as n approaches infinity, absolute value bar. Change all your n's to 1 more. I always said n plus 1. I should be saying 1 more. So 3 to the n plus 1, and then negative 2 to the n plus 2 times n plus 1. Did I do that too fast? Does everybody understand why n plus 1 became n plus 2? It's n plus 1 plus 1 more. Now we multiply by the reciprocal of what we were starting with, negative 2 to the n plus 1 times n over 3 to the n. Close it. All right. What are the 3's going to do? And leave what where? 3 on top. Okay. Now the negative 2's probably are going to do something similar, except for the fact that they have different exponents this time. So let's kind of play with this for a minute and see what's going on. We have negative 2, n plus 1, negative 2, n plus 2. Plug in a 2 to be negative 2 to the 3rd over negative 2 to the 4th.
1/2.
It leaves a negative 2 on the bottom, doesn't it? Does that make sense? So it doesn't matter. What matters is the fact that they're 1 apart. So that means there's 1 left over. Does that make sense to everybody? Okay. So
leave a negative 2 n plus 1 on the bottom?
no, just a negative 2. It just leaves a -2 because no matter what number you plug in, the bottom one will be one more than the top one. So when you cancel them, there's one left over on the bottom. Okay, so this time we have something that looks very similar to the last problem. We have 3n over -2n plus 1. Go ahead and distribute, -2n minus 2. Do I need to do L'Hopital's again? Yes. So the numerator will be 3 and the bottom will be -2, but remember I'm in absolute value, which means that the final answer is 3/2. So is that bigger than 1 or smaller than 1?
Bigger.
Bigger. Therefore the series does what? Diverges by the ratio test. Now we're going to go down a road that we haven't gone down before. We're going to deal with a new numerator. Look at number 7's new denominator. Excuse me. What's the denominator of number 7? N to the n. We have never dealt with that in this class before. And something unusual is going to happen. So we started off just like before. So we have limit as n approaches infinity of, now what's the top going to be with the factorial? N plus 2 factorial over n plus 1 to the n plus 1. They both change. Now we're going to multiply by n to the n over n plus 1 factorial. Okay, I'm probably good with the factorial, and I believe you are too. We haven't done it with n plus 2 and n plus 1. Which one's bigger? N plus 1 or n plus 2? N plus 2 is bigger, right? So we start with n plus 2. What's the next one down? N plus 1. That matches on the bottom, so we can mark those two out. So I'm left with n plus 2 on top. Agreed? Okay. Now, I'm going to do something a little bit unusual to clean up the n plus 1, and nn. So, I want to show you something. I am going to break this n plus 1 to the n plus 1 into its two components. This is the same thing as n plus 1 to the first times n plus 1 to the n. Do you agree with that statement?
Yes.
Because you just add the exponents. The reason I'm doing this is because I want the top and the bottom to have the same power, and that power is n. Okay? That way, I'm going to pull that aside for a minute. So I have n plus 2 over that leftover n plus 1. Then I have n to the n over n plus 1 to the n. Let me put this back where it was. Hang on. Get off of there. This became the denominator. So we now have limit as n approaches infinity of n plus 2 over n plus 1 times, now when two things have the same power, like if I had 3 squared over 5 squared, is that the same thing as 3/5 squared? Can I do that? Is that legal?
No, because the base is different.
Well, no, you can't.
Yes, you
Yeah.
can do that.
It is allowed if the powers are the same. If the powers are the same, you can make it in one fraction with just a single power. And that's what I'm going to do right here. N over n plus 1 to the n power. Okay? And that right there, as a limit, equals a number that you probably haven't seen before. Well, actually, you've seen the number, you just didn't know that this was the limit of it. So right now, I'm going to take my calculator and show you something. I'm going to take this fraction right here, and I'm going to flip it over. N plus 1 over n to the nth power. And I'm going to take the limit as n approaches infinity of that part. I'm going to flip it over. Because if I leave it the way it is, you're not going to recognize it. If I do it this way, you will. All right? So now, I have put this equation into y equals. Do you see that?
Yes.
Okay. I'm going to go to the table. And way back at the beginning of the school year, when we first started limits, One of the ways we did limits as x approaches infinity is we put larger and larger numbers into the table to see what happened. So watch what happens when I put 1,000 in here, and then 10,000, and then 100,000. Does that decimal look familiar?
That's easy, right?
That is E. And that is actually where E came from. It is the limit as n approaches infinity of n plus 1 over n. It equals E. Okay? Now, the more common way that it is written is this way. 1 plus 1 over n to the n. Okay? Back in Algebra 2, long, long ago, you learned a formula that looks like this. Does that formula look vaguely familiar?
Vaguely.
Vaguely. Compound interest is what it is. You know, the interest is compounded monthly at 7%. How much will you have after 10 years? You know, things like that. What happens is, if the R becomes a 1 and n approaches infinity, that's where the E comes from, and that's what created the PERT formula. Do y'all remember the PERT formula? That's called continuously compounded interest. So n is how many times a year you get interest. If it's infinity, it creates an E. And that's where the formula applies as far as compound interest is concerned. So I'm taking a little bit of a detour to kind of give you a little history of E, but that's where they came up with E. It was this limit right here, and they came out and they found it coming up in so many different places, they decided to give it a name and they called it E. So, now, what's the difference between this and this? This is an E. What is this?
Inverse E. Oh yeah, inverse E.
It's E. It's inverse E, or actually more reciprocal of E. Okay? This is 1 over E. This limit right here is 1 over E because the fraction's upside down. So we now write that this is going to be, what is this limit going to be? That part alone by L'Hopital's rule. What's it going to be? 1. So this is going to be the absolute value. 1 times 1 over E, which is 1 over E. There's our number answer. Now the question is that less than 1 or greater than 1? What decimal does E start? What is this? How does it start out? 2.7. So 1 over 3. That's less than 1. Therefore, the series converges by the ratio test. Didn't leave me a lot of room to do that one. Now, this one doesn't work well with polynomials, this test. Okay? It works when powers are weird and factorials and stuff. This is inconclusive most of the time with polynomials. So I underline inconclusive with polynomials. So if you see polynomials, don't go this road. Choose something else. But almost everything else works beautifully with ratio test. Okay? Now, the last test only works with a very small group of problems, but it's so easy. And it's called the root test. You're looking specifically for powers of n. In other words, nth power. Anytime you see nth power, especially around the whole problem, root test is what you want to do. It just makes it so nice and easy. Okay? So the way it works is you take the absolute value of the function and you always raise it to that power, 1 over n, always. And you clean it up. And it's the same results as before. If the limit is less than 1, it's convergent. If the limit is greater than 1, it's divergent. If it's equal to 1, it's inconclusive. Now, they also tell you that it can be shown by L'Hopital's rule that this is equal to 1, the limit of n to the 1 over n. And I'll do a problem with that in it and show you that it does. So if you see that, you can just automatically say that's 1. Just like we can now automatically say the other one is E. Okay? So let's look at number 8. Notice that both of these are the powers of n. That's why we want to use this test. So what we're going to do is the limit as n approaches infinity, absolute value, take the problem as it is and raise it to the 1 over n. Note, changing to n plus 1s or anything like that, not with this test. We just copy it down, put it in absolute value, raise it to the 1 over n power. And I will show you how wonderfully easy this is. When you have a power and a power next to each other, what do you do to the exponents? Like x squared cubed? You multiply them. It's x squared to the third is x to the sixth. So here I'm going to multiply 2n times 1 over n. What does that equal? 2. So this is the absolute value of 2 squared. I don't have n's anymore. What about the denominator? The power of n and the 1 over n power, they cancel each other out pretty much. Leave a power of 1. So there's still the n that's the base on the bottom. Can I plug infinity in and get an answer? Yes. What is 4 over infinity? 0. And that is less than 1. Therefore, the series converges by the root test. Okay? Look at the next one. See that big power of n on the outside? That's your key. That root test is the best for this one. So we're going to copy the problem down. We're going to do the limit as n approaches infinity, absolute value. Make sure you put this in a parentheses. 4n minus 3n to the third over 5n to the third plus 1 to the n. Then close your absolute values. And then put the 1 over n on it. So what's going to happen to the n and the 1 over n? They just cancel out. We're done. So we have absolute value of 4n minus 3n to the third over 5n to the third plus 1 equals. All right. I'm about to tell you something. Some of you probably already know this. But I'm going to show you a way that you can save a ton of time from having to do L'Hopital's multiple times. Okay? Do you guys remember what it means to say the degree of a polynomial?
Yes.
What is the degree of the numerator? 3, because the highest exponent is 3. What's the degree of the denominator? 3. If you're taking a limit as n approaches infinity and the degrees are the same, the leading coefficients are going to be the answer, negative 3 over 5. When all is said and done, that's what it's always going to come out to be, as long as the degrees are the same. The degrees are not the same, probably want to go L'Hopital's rule. Okay? But that's the way it always works. So this cleans up to be 3/5, which is less than 1. So what's happening? Converging or diverging?
Divergent.
Look at the box. Let's make sure. If L is less than 1, which it is, it's absolutely convergent. The series, oops, I forgot to write the word series. The series converges by the root test. Now, I want to go ahead and do the last problem because that thing that we boxed in right here, this n to the 1 over n, that's going to show up here. And I want to show you how to handle that. Okay? So we have the limit, I'll draw a line right there. N approaches infinity, absolute value of negative 2 to the n over n to the fourth to the 1 over n. So what's going to happen on top? What's it going to clean up to be?
-2.
Just negative 2, right? Because the n and the 1 over n are going to cancel for the top. So this is the limit as n approaches infinity of just negative 2 on top. And the bottom, I'm going to multiply the exponents. So this is going to be n to the 4 over n. All right. Now, stay with me as I walk through this one. This one up here says n to the 1 over n. Agreed? So what I'm going to do is I'm going to take this thing and write it as n to the 1 over n to the fourth, because that's the same thing. I just broke it back apart and kind of switched the exponents. So the limit for the bottom is going to be 1 before I talk about the 4. But what is 1 to the fourth power? Just 1. So the power of 4 doesn't really do anything. So the answer is going to be the absolute value of negative 2 over 1, which is 2, which is greater than 1. Therefore, it does what? I'm hearing both. Diverges by the root test. Yes, sir.
Regarding was the n raised to the 1 over n and then the 4 on the outside.
Uh-huh.
You said that like the 4 doesn't really do that. Ultimately, 4 doesn't do anything. But so even if we just came across it like that, we would have to multiply the 4 into it, wouldn't we?
What I was, okay, basically what I was showing you is it doesn't matter what's on top of the fraction. It could be 1 over n, 4 over n, 9 over n, it doesn't matter. The limit's still going to be 1. I was just showing you why it works that way. Okay, so from now on, you don't have to separate it like this, but I'm just showing you that even though the top was something different, the limit is still going to be 1 because it's 1 to a power. Question?
How did you, I understand how you got 1 in the denominator because of the rule that it says right there.
Mm-hmm.
But how did the -2 stay on the top?
Okay, the on the top, the n and the 1 over n, right here,
No.
that's what I'm saying. That's this, you do each one individually. That right there, that's the limit is -2 because the n and the 1 over n cancel each other out. Okay? Then I raise this to the 1 over n, that takes care of the bottom. So the limit of a -2 is still a -2.
I thought we did we not do the L'Hopital's rule?
No, we're not doing L'Hopital's at all in this problem. Okay? We're just using this special limit right here, showing that that's equal to 1. Okay? Any other questions? Alrighty.